Hello everyone. So this video is Julia Olefination, where we will see how we can make CC double bond, and there will be also the discussion related to the modified version of this reaction, which we call modified Julia, and then also the more developed version of modified Julia, which is Julia-Kociensky olefination. So let's start. Julia Olefination. So here you can see the product is E-alkene, right? And two colors I have used, from which you will be able to understand that this is actually a connective CC bond synthesis, double bond synthesis, because the CC double bond, it is formed by joining two separate molecules. But here we cannot see two separate molecules. Instead you are seeing this one, right, where Lg is written. Now Lg may be OAC, that is leaving group, or it may be OCOPH. So as you can see, two different colors, that means this CC bond is formed between the left hand side molecule and the right hand side molecule. So let's see how we can make this molecule from which the elimination is actually occurring. So here we can see still two separate molecules you cannot see, because step by step I am going backward. So this Lg, the previous version is O minus. That means when the O minus, which is beta alkoxy sulfone, because this is, if you consider alpha position with respect to the sulfone group, then this is the beta position. So beta alkoxy, and this alkoxy in presence of Ac2O, acetic anhydride, or benzoyl chloride, PHCOCl, it will be converted to this Lg, which is OAC or OCOPH. Now we will see, if you move further backward, there is a aldehyde, that is this blue molecule, and we have this carb anion. Now this carbanion is formed from RCH2SO2PH. Now these two hydrogens, they are acidic enough because of this group. In presence of some base, which may be butyl lithium, lithium diisopropylamide, LDA, or it may be some Grignard reagent. So there will be formation of carbanion, and this carbanion, it will attack this aldehyde. So these are the two separate molecules from which finally you are getting this E-alkene. So the pink part is coming from this RCH2SO2PH, and the blue one is coming from this aldehyde. So that is why we are calling it connective CC double bond formation, because ultimately we have used two separate molecules. That is from initial point of view, if you consider. Now if we see the steps, what are the name of these steps? Here this step is reductive elimination. Details of this step mechanism we will see, but the name is reductive elimination, and this step you can call it esterification of or O derivatization, because O minus is converted to some good leaving group, OAC, OCOPH, esters are formed. And this step is addition. That means the carbanion that is attacking this carbonyl group, and there is also a CC bond formation. So that is why addition reaction or CC bond formation. And the initial reaction is metallation, because here this H is replaced by some metal. So there is a metal depending on which base you have used. So suppose if it is lithium, it will be minus and Li plus. So that is why it is metallation. So these are the steps. First metallation, then addition reaction, then esterification, and finally reductive elimination. So step 1, we have considered addition of phenyl sulfonyl carbanion, that means this moiety, to an aldehyde. So this is two steps. Suppose we have combined the metallation and the addition reaction, and there is esterification. So suppose all these three steps we are considering under step 1. So in step 1, in presence of this base or some other base, here we have taken butyl lithium, carbanion is generated along with the metal ion that is present. This carbanion, it will attack here. Then you, and two steps are shown here together. In presence of Ac2O, this O minus will be converted to Ac2. Now there are two phases for addition of this carbanion to this carbonyl. So that is why two possibilities of two diastereomer. As you can see, these two are diastereomer, but I have also written here plus its racemic form, and also plus its racemic form. That means here you can see both these are above the plane. So racemic form means both will be below the plane. Similarly, for the second diastereomer, the racemized form is this one will be now below the plane and this one will be above the plane. So these are the possibilities, because carbanion can attack any of these phases of aldehyde, right? Now the second step is reductive elimination. Actually you can also call it total 3 steps, but just for make it concise, here we have reductive elimination. Now this is very interesting because whatever is your diastereomer, it doesn't matter at all, because the intermediate carbanion that you are getting in presence of this reductive elimination, the reagent is sodium amalgam, this SO2 pH group is removed and in the same place we have now negative charge. Now see, I have used this type of bracket, that means whatever is your diastereomer doesn't matter, there will be a common intermediate. So this is the likely common intermediate and it will arrange itself in such a way that is its lifetime is such that it will be able to arrange in a way so that it can achieve the low energy conformation. So this is the low energy conformation. These two are actually same. There is equivalent sign where the negative charge and the OAC, they are opposite to each other. So this type of conformation is necessary so that elimination can occur in a better way, right? And these two groups, they are far from each other. So that is why we have to say that this will have some lifetime so that R and R prime, they can be far apart from each other. So that is the reason we are getting ultimately E alkene. So whatever is your diastereomer, so that will not create a problem. So this is very that is important feature of this Julia Olefination. Now this reductive elimination, how this SO2 pH group is removed and instead you are getting this negative charge, we will see in detail. So this is the details of reductive elimination step. So this is our pH SO2 group, right? So in presence of sodium, it will give 1 electron, and suppose one of these sulfur oxygen bond, if it is broken, there are 2 electrons, 1 electron over sulfur, 1 electron over oxygen, and 1 new extra electron is coming from sodium, so there will be a negative charge. Now this is anion radical because it has negative charge as well as dot, that is radical. Second electron transfer from sodium. Now the same event will be repeated. Another sulfur oxygen bond, if it is broken, now there will be 2 electron over sulfur and negative charge over oxygen, right? And finally there will be, this is dianion, finally there will be formation of SO double bond, and this sulfur carbon bond will be broken. There will be negative charge at this carbon. So in this way we are getting this pH SO2 minus is removed, this portion is removed, and we are getting carbanion intermediate. So this carbanion intermediate you have already seen in the previous slide. Now some important features of Julia Olefination. The first point here we can see stereoselective E alkene formation. So whatever is our diastereomer, it doesn't matter. It indicates that the alkene forming step for both diastereomeric sulfone, remember the intermediate, it must involve, not intermediate, I mean the first formed product. It must involve a common intermediate. So that is why it is not stereospecific. Stereospecific means suppose there are 2 diastereomer, A and A prime. From A you are getting one isomer, from B you are getting another isomer. No, it is not like that. From both we are getting same. So we cannot say it is stereospecific. Okay. So this is common intermediate, and this carbanion intermediate, regardless of its original configuration, it must have some sufficient long time. Otherwise, how it will adopt the low energy conformation? So if it is not adopting low energy conformation, there is a chance of getting mixture of alkene, but that we are not getting. So it proves there is a sufficiently long lifetime involved here. The E selectivity improves as a function of increased branching in the substituent. So that will vary depending on what type of substrate you have taken. It is also regioselective because see here ultimately we are removing pH SO2 group or OAC group depending on what esterification we have, pH SO2 group we are removing along with OAC or pH CO2 group depending on which esterification you have done. So it is selective, it is not removal of some hydrogen or OAC, hydrogen or pH CO2, because there are so many types of hydrogen can be present, acidic hydrogen, but that we are not doing. We are removing pH SO2 along with OAC or pH CO2. So that is why it is regioselective. Only the alkene with CC double bond will be formed or will be joined. That involves the 2 carbons. Which 2 carbons? One carbon which is carrying this group, another carbon which is carrying the LG, that is OAC or pH CO2. So that is why it is regioselective. Now this is a very good alternative for Wittig olefination, because see, in Wittig olefination, which is the Soslan modification where we get trans alkene, this sulfone, this is a good alternative. And another important point, if we compare with Wittig, the sulfone here that we are using in this reaction, they are more easily purified than the phosphonium salt which you do in case of Soslan modification, that is Wittig olefination. So that is why purification part is easy, and also it is readily available as a starting material. So these are the advantage you can say compared to Wittig olefination. Now preparation, or if you want to prepare tri or tetra substituted alkene, in the previous example you have seen R prime, so it is simple, only two substitution. But suppose tri or tetra substituted alkene we are trying to make via this sulfone route. Now that is limited. Why it is limited? Because now the beta alkoxy sulfone that you will get by the addition of sulfone anion to ketone. In the last example we have used aldehyde, we have not used ketone, but when there is ketone there will be one extra substitution if you want to increase substitution. But what happens when addition of sulfone anion to ketones, there is a possibility that they are prone to revert to the starting material because of this increased substitution. So that is why most of the example you will see it is mainly involving the aldehyde, not the ketone. So tri or tetra substituted alkene we can make, but that is limited compared to disubstitution. Disadvantage is low tolerance of reducible functional group. Remember in the last elimination, reductive elimination step, we have done this reduction, that is reducing condition present. But if any group is present in your starting material where that is reducible functional groups are present, then that will also be reduced. But that we do not want. We want them to be intact. But if it is reduced, that is obviously disadvantage. And this is the very important disadvantage, is that it is not one pot synthesis. First you have to do CC bond formation, you have to generate carbon and it is attacking the aldehyde, then there is a O acylation, then there is a reductive elimination, and you are getting finally the product. So it is not one pot synthesis, right? So this is the disadvantage. Now to what is the solution? The modified version next we have to discuss, where you will see this second disadvantage we can overcome, and also there is no such reductive elimination, that is no reducing agent will be used. So in this way these disadvantages we can overcome. Modified Julia. So what is the difference with the previous version? So in this case you will see, instead of using pH we are using BT or benzothiazole. Now in this case we are using this type of base LDA, and there is the further two steps. Remember the O acylation, that is esterification step, and the reductive elimination step, that is not present. Now here in a single step you are seeing we are getting alkene, but here we have another disadvantage for this modified Julia, is that we are getting mixture of alkene stereoisomer. So when you will see the detailed mechanism, it will be clear to you why we are getting mixture, why we are not getting E, as we have seen in the previous case. But here this advantage we have obviously overcome, and that is we are using this benzothiazole group. So that is why you don't have to do O derivatization, or you don't have to do reductive elimination. You just have to use base, only reagent we are using some base, and this part will be removed in the form of leaving group. So this oxygen you can see now it is a part of this leaving group. From the color that we can understand, and SO2 is another leaving group. Now we will see the mechanism. So this point I have already mentioned, it alters the reaction pathway. No acylation, no reductive elimination. So it is a one pot reaction, unlike the previous original classical Julia olefination. So here what we are doing, in presence of LDA there will be metallation, that is there will be negative charge generation in presence of base, and that will attack, right? Now as it can attack from both sides, right? So that is why there will be possibilities that two diastereomer will be formed. Okay, though the stereochemistry I have not shown, but possibility is there. And unlike the previous version, you have seen there is a common carbon and intermediate, that is not happening here. So that is the reason the initial attack of this carbon, whatever mixture of diastereomer will be there, that will be maintained ultimately. So that is why we are not getting particularly E alkene. Though it is true that It depends on reaction condition, and you can see some research paper where depending on what reagents are used or some substituents in the starting material, there can be some stereoselectivity, but in general we cannot say that we will get E alkene only, unlike original Julia Olefination. So finally what is happening, we do not have any pH group. So this group, it is more that is electron deficient. So this negative charge, it can attack at this carbon. Okay, so this is the something happening which we have not seen in the original classical Julia Olefination. Now when it is attacking, there will be negative charge generation over this nitrogen, and finally there will be this CS bond will be broken. Now this is spontaneous Smiles rearrangement, where this heteroaryl group, that is this benzothiazole group, that will be migrating from sulfur to oxygen. So this is now attached to sulfur, right, CS bond. Now it will be attached to the oxygen. See how it is happening here. This negative charge, it will again make CN double bond, and this CS bond is broken. So finally this group is now attached to oxygen. So that is why it is spontaneous Smiles rearrangement from sulfur to oxygen, which we have not seen in the previous version, original version, right? So because of this electron deficient nature of this heteroaryl group, we are getting different mechanism, and there will be removal of this SO2, that is gas. There will be CC double bond formation, and this will be removed. So finally we are getting mixture of alkene Z and E. And remember, this is a good leaving group. Okay. So in this variation of Julia Olefination, that is the new version, there is no equilibrating intermediate, and that is the reason that stereochemical outcome, that is the result of the stereochemistry of the initial carbonyl addition. So this is, I am talking about this addition that will decide the ultimate stereochemical outcome. Now here we will see the role of bulky bases. We have used LDA. So this is the structure of LDA, right? Lithium diisopropyl amide. Now these two groups, if it is replaced by this type of SiMe3 group, now the name is changed. So both are actually same molecule, but I have mentioned both the names because sometimes if you are seeing some new reaction and instead of LIN SiMe3, which is the detailed structure, suppose this name is given so that you can understand what this molecule is actually. So when we have replaced this isopropyl group with this type of large group, what happens? Now this is bulkier than original LDA, and hence it is more selective than LDA. So the good point of using bulky base is that it reduces the chance of nucleophilic attack on the benzothiazole, because this is very electron deficient heteroaryl system. So suppose the base, if it is not very bulky, it can attack this. There is a chance it will also attack this benzothiazole moiety. That we do not want. So that is why we use bulky bases. And if this lithium is replaced by sodium, then the name is changed NaN-SiMe3 whole 2 or NaHMDS. And if it is replaced by potassium, then the name will be like this. So I have mentioned all these reagents so that you can understand this is the reagent for the modified Julia Olefination. Now some more interesting feature. There is further development of this process. Now that is this principle of modified Julia Olefination, we can extend it further by changing this heteroaryl system. So you can see here various heteroaryl system, though these two are benzene related, but rest of them they are heteroaryl system, right? So Bt benzothiazole, you have already seen it. There can be pyridine or pyrimidine. This X can be H or N. Then there is some electron withdrawing group attached to aromatic ring. So basically what we are doing, we are making this aromatic system more electron deficient by adding some electron deficient group, right? That is the purpose. And there is also some tetrazole system, 4 nitrogen in a single ring. That means you can understand how electron deficient it is, right? So tertiary butyl tetrazole, phenyl tetrazole. Our purpose is to make it heteroaryl system as electron deficient as possible, so that the negative charge over oxygen, it can attack this heteroaryl system at this point, right? So that is the purpose. Now out of this system, it is observed the most important one is the PT system. So this is our PT system, and it is introduced by Kociensky et al. And that is why we have a new reaction, which is Julia-Kociensky reaction. So here what happens, diminished side reaction such as homocoupling. Sometimes there is a homocoupling between the two heteroaryl group, that chance is reduced, which is sometimes seen in case of benzothiazole, that chance is reduced. And also here you can get better selectivity. Remember, in case of benzothiazole, though we have overcome some disadvantage, it is one pot, there is no reducing agent we are using, but still there is no selectivity, but that now we can overcome when you are using PT system. So now we have this Julia-Kociensky olefination, where the heteroaryl system is like this, which in short we are calling PT. In presence of this type of bulky base, first as usual the reaction mechanism is same, so I am not showing it in detail. So it will attack this carbonyl group and there will be negative charge, and this negative charge it will attack here, and rest of the mechanism it is just like the modified Julia with benzothiazole that you have already seen. So finally but here we have E alkene, that is the beauty, and SO2 is the leaving group, and this is a good leaving group, right? So this is Kociensky olefination reaction. So that's all for this video, where we have seen the original classical version of Julia, but there is further development, modified Julia, where the heteroaryl system we have used, which is benzothiazole, and there is further development where the heteroaryl system is like this, which is very electron deficient, and that is by this type of Smiles rearrangement, which starts by this attack of O- to this carbon, and that will be enhanced. Okay, so I will leave this video with the hope that it will be very informative video for you. Thanks for stopping by.